All right. Thank you, Ozma, for introducing me. Again, my name is Richard Gwynn, and I'm a graduate student here at Western. The title of my thesis is, sorry, I was trying to get everything ready. Okay, Investigations into Mercury's Mantle through the Partial Melting of Encetate Chondrites, or chondrites. Uh, as you just heard, Ozma is my advisor, and then on my committee was Christina and Sean, or Dr. Wolowski and Dr. Mulcahy. All right, so to start with a little location, Mercury is the innermost and smallest of our system's planets. This is a to-scale image, so it's very small, and the sun is very big. So in exploration history, there's only been 3 missions to the planet. Mariner 10 was in the early 70s and photographed only about 45% of the surface, but did discover a magnetic field. Messenger, which is most of the data we'll be using, is uh, completely map the surface and as well gained compositions for magnesium over silicon and aluminum over silicon, as well as many other elements, but not full. We'll talk about that again. And then Bepi-Colombo, which is set to arrive in late 2025, is going to give way more detailed insights into the surface composition, magnetic field, and exosphere compositions. All right, so we're going to be using Messenger's data, and I thought it might be useful to show how it's collected. Messenger had equipment on it that was able to read the composition of the surface, and it did it similar to how a SEM works, except the energy source is the sun. The solar X-ray radiation bombards the surface, excites elements, and then you're able to tell what element it is based off its energy. And in the quiet sun, or essentially no solar flare, it was able to pick up magnesium, silicon, and aluminum, but it didn't need a flare for heavier elements like sulfur, calcium, titanium, and iron. There were challenges to mapping the southern hemisphere, however. Messenger had to be in a very elliptical orbit, as you could tell from this image. And that orbit definitely limited the southern hemisphere coverage because it was very far away from it while it was taking in information. So it ultimately results in a lower resolution map of the southern hemisphere. So initial insights from Mercury's crust show that there's very low FeO, around averaging 1.5 weight percent, and elevated levels of sulfur, which is a lot more sulfur, up to 20 times more than Earth's surface has. The surface is heterogeneous chemically. It also has various geochemical provinces. You can tell some of them from the images here, like the HMR region for the magnesium over silicon graph. And then Mercury is a highly reduced planet, and we could tell that from a few things. One, it has an incredibly large core that's iron rich. With so little iron or iron oxide on the surface, it points to a reduced planet. And we'll talk about the iron woostite buffer in a little bit, but very reduced, minus 6.5 to minus 2.6. All right, so the geochemical terrains that Messenger saw on the surface uh, exhibited very diverse compositions, significantly different. They were determined through magnesium over silicon, aluminum over silicon, and calcium over silicon differences. And those major terrains are listed here in color order, so you can see them on the map, as well as their compositions. Which brings us to one of our first questions, which is, why is Mercury's surface heterogeneous to begin with? And what could oxygen fugacity have done to contribute to the production of these heterogeneities? All right, so Mercury is the least oxidized terrestrial planet. On the left here, you'll see FeO weight percent in the mantle, and Mercury's hovering around that 5 lower 2.5 to 3%, where as you go out heliocentrically from the sun, it gets more oxidized and it gets more in there. And then we can reverse this graph to look at the size of the cores of these planets, where Mercury's is close to 55% of the volume or 70% of the mass. So it's a very large core compared to other planets, meaning there's more native iron or iron metal in Mercury than in Vesta, which then increases the ratio as you go out from the sun of how much FeO there is compared to iron. So starting to talk about oxygen fugacity. Oxygen fugacity is essentially the amount of oxygen that's available in a system. A low oxygen fugacity means very low oxygen or reduced, where an oxidized system would have more oxygen. And we did this by expressing it through the iron woostite buffer, which is shown in these formulas here, where X is going to be our concentrations and lambda is our activity coefficients. Most rocks on Earth are measured with a QFM line, which you can see on the top diagram here. Iron woostite is about 3.5 to log units lower, so it's already much more reduced. When you can see Mercury is another 6 log units lower than the iron woostite buffer, or up to 6 units lower. Again, showing that Mercury is very reduced, very low FeO on the surface, and again, that range of IW -6 to -3. So some of the effects of low oxygen fugacity is going to be the activity of silicon. Data from experiments similar to this graph show that silicon metal stabilizes in reduced environments. So the more silicon metal you have, the more reduced the environment is. This would mean at the low FO2 seen on Mercury, silicon would be preferably partitioned into the core, depleting it from the mantle. Silicon is a major rock forming element, which brings up our second question, which is, can low oxygen fugacity affect the valence state of silicon in the mantle itself? And how would magmas vary in this case? We're going to be able to determine possible source materials, which is my main hypothesis and question that I started with, based off of chondrites, which are essentially meteorites from the beginning of the solar system. They're primitive meteorites that did not experience igneous differentiation, and so they are representatives of the early solar system itself. We were looking at between instatite and CB chondrites, which if you look at the far right graph, you'll see that Mercury actually falls in that CB field. However, CB chondrites lack necessary volatiles, as well as CB chondrites are now believed to be a broken up planetesimal core and not a chondrite. So we looked at instatite chondrites instead. Instatite chondrites are very reduced. They're in line with Mercury's lava. So you can see the EH4 right around the IW -6 in the bottom figure A, and it's lining up with Mercury's lavas. But as well as other volatiles like sulfur, sodium, and potassium match as well. So my main hypothesis is I believe that EH chondrites would be a good candidate for a building block of Mercury. And is Mercury's mantle similar to an EH chondrite? So again, those are the key questions, which is what caused the surface heterogeneity seen on Mercury? Can low oxygen fugacity affect the valence state of silicon in the mantle itself? And what are Mercury's building blocks? And I believe them to be EH chondrites. So for one, we need to know what Mercury's mantle composition, and there was previous research on this topic, although only one time, and that was this paper that used Messenger's surface composition to make a mineralogy of the surface, and then use multiple saturation points to be able to determine depth and composition of the mantle itself. It was found to be lersilytic with different fractions of clinopyroxene. So in that previous study, they used surface compositions to gather multiple saturation points to then guess Mercury's mantle composition. Whereas in our project, we're going to be melting EH chondrites, specifically the Endark meteorite, and then essentially recreate planet formation and differentiation. So we're going to fully melt it and then see what happens with subsequent cooling, and then try to match that to what we see on the surface to see if we can find a model that best fits what we actually observe. So our starting compositions for this experiment are going to vary because I'm doing thermodynamic modeling and high pressure experiments, or I have done. I guess I'm not doing anything. The starting compositions are all going to be EH4 chondrites with varying redox state. We're going to represent that redox state by how much Si metal is there over SiO2. That ratio increases the more reduced it is, similar to this figure here, where it shows that the more Si metal there is, the more reduced it is. For P-melts calculations, we're going to vary so we can cover a wider ground. And by doing that, we're going to convert the SiO2 in the silicate to Si metal, which pulls it out of the mantle and allows us to keep the same silicon budget because I'm not actually removing silicon, I'm just changing its state. So there's going to be 5 compositions for P-melts, and then last bit on P-melts is that it can only model the silicate composition. It cannot model the metal or sulfide. However, in experiments, I'm only going to do one composition so I can check varying melting states, and that's going to be the same EH4 composition. However, it's only going to be the one, which is the 0.55. And briefly, that's what the difference in these compositions. I can come back to this later. I just wanted to be able to show the difference in the mass fraction of the metal and silicate phases, as well as how much silicon is actually being pulled out of the silicate. Starting with the actual EH4 at 62.6% SiO2 all the way down to 43. So essentially 20 weight percent SiO2 being pulled out of the mantle. All right, so the mineralogy of the starting composition shifts dramatically due to this silicon ratio. At lower oxygen fugacities, or a higher SiSO2 ratio, there's more magnesium oxide, where at more oxidized environments, you're going to see more SiO2. The estimated mineral composition that we talked about earlier from the paper are these blue triangles that sit in between the 0.17 and 0.24 ratios. 0.17 representing a 5 weight percent silicon metal and 0.24 representing a 10 weight percent. Again, silicon is a major rock forming element. Thus, this is important that FO2 definitely is altering the mineralogy significantly and therefore melting properties. For our experiments, I did them all at 1 GPa or 10 kbar between 1300 and 1650 degrees Celsius using a quick press piston cylinder in our planet formation lab, which is a really cool lab name. Then again, the thermodynamic modeling or P-melts, here's the version, and I batch melt the EH chondrites there. So from 100% melt down to completely cooled. I'm then going to take all of this data and try to compare it with Mercury surface, hoping to answer major questions like, can I match Mercury surface to my experimental melt? All right, so the reason I'm doing 1 GPa is from this figure here is from the same paper that we got the MSPs from. And this shows that the average pressure of the mantle melting was around 1 GPa. And it also helps that P-melt's predictions become less accurate over 1 GPa, so it seemed like solid ground to start on. All right, so starting with our results, I'm going to start with my P-melts models because there's a little more to talk about. The first thing I noticed was that the increase of Si metal, or the higher the SiO2 ratio, the higher the liquidus. It moved by a total of 80 degrees Celsius. The degree of melting curves are definitely affected, and then the cooling rate is different for each model as well. There's also changes in mineralogy. I think this one shows the most dramatic shift, especially, but starting out with olivine is the primary liquidus phase, meaning it fractionates first in all experiments and all models. The change of mineralogy is a direct result in changes of silicon content, starting with more oxidized systems like the 0.07 model is going to be higher in clinopyroxene fraction, which you can see with the gray bars, and then dramatically shifting to where it's almost completely olivine down at the 0.55 ratio. So reducing conditions stabilize olivine and over CPX, OPX, and feldspar. Another thing to say is that the 0.55 model actually has different minerals in general, not calculating feldspar or OPX, but instead nepheline and spinel. All right, so looking at this 0.07 model to be able to see a little bit better, I looked at this one in particular because due to the oxidation of my experiments, this is a close model to what we actually see in Si metal from the experiments, which is around 1.5 weight percent. And you'll see that feldspar and clinopyroxene both melt out at 15 weight percent melting or 15% melt, while OPX is around 60. The behavior of sodium and or Na2O and K2O shift with the composition of feldspar, going from an albidic to an andesine composition. And then this is the P-melts model for 0.55, which is the starting composition for the experiments, where SiO2 increases rapidly in the beginning due to nepheline and CPX melting, and then decreases slowly with olivine melting. CO initially increases with melting and then decreases as CPX melts. That's due to the augite or the shift in augite composition that you can see in the bottom figure. I wanted to include the 0.07 points, and I'm sorry they're so small. There's so many points and they overlap so badly. This is really the only way to be able to see that there is an overlap. All right, and these are my two good examples of my experiments that came out. The one on the left is superliquidus or above the liquidus, and it's at 1650 Celsius. It only had 3 phases, a silicate melt, a metal, and a sulfide shell that encapsulates it. You can not really see the sulfide here, but I'll zoom in shortly. You can see the sulfide a lot better in a subliquidus where I zoomed in more. And this is at 1300 Celsius, where there's 4 phases, and then some phases even had a OPX, but only 1. So just to show the phases and textures again, low temperature experiments yield up to 5 phases, the melt, metal, sulfide, olivine, and OPX. Silicate melts display glass and dendritic textures. Dendrites are really common at high pressure, especially with rapid quenching. Metals form spherical shapes, which you can kind of see here, and it actually has a cool technical name of blobs. Sulfides often make shells around that metal, and olivine shows both euhedral and subhedral grains between 15 to 200 micrometers. Here's some zoomed in photos to let you see the metal blobs a little better and the sulfide encapsulation in the fully melted sample or experiment 18. And then on the right, I just want to be able to show some good dendrites where the darker dendrites are Mg rich and the lighter areas are Mg poor. This one was at a really high temperature, so there's actually metal trapped in some of the dendrites, which is just cool to see. And then here, there's actually dendrites inside the metal as well. It's very zoomed in, but you can see, and it might be hard to tell, but the Ni poor alloy areas are going to be the darker dendrites, and the lighter areas are going to be nickel rich. And then there's just a small sulfide blob down in there. And then the image on the right, I just really liked because of thinking of planet formation in general. When a planet forms, the core forms by diapirs falling down into the core and building it. And it kind of looks like that here with the larger metal in the center with the diapirs of metal falling down. So to conclude about the experimental phases, olivine is the liquidus phase again, and the liquidus temperature is approximately 1600, and that's because we have 1% olivine at 99% melting, while 100% melt obviously did not show any silicate minerals, and then there's olivine present in all the other ones. The average oxygen fugacity, although the samples were oxidized, still averaged at negative or IW -5, which is right around the mercury area, so we're still good there. And then also the heating time durations are going to be go up for lower temperatures. And that was just to make sure I allowed time for diffusion of elements to fully conclude. So here I'm able to compare P-melts and mineral assemblage, or P-melts and experiments mineral assemblages. Experiments are going to, again, only show OPX once, mostly only having olivine, while P-melt still predicts feldspar, OPX, and spinel. Another interesting point down here is that P-melts predicts a 40% melt at 1400 degrees C, while experiments are only predicting a 14% melt. There's a large gap there. Here are oxide compositions. I don't want to bog down in this too much, but in general, SiO2 decreases and MgO increases with temperature. There's very different levels of sodium potassium compared to our P-melts and EH chondrites. We'll definitely be talking about that later. And then something else to think about is that my starting composition was oxidized during the experiments. I started at that 0.55 ratio with 18 weight percent silicon metal and ended up with around 1 weight percent average. That was due to failures in the casings and just due to high temperature and pressure. We ended up fixing this later on, but we'll talk about that as well. But then again, FO2 is still very reduced here. So the red line here represents a P-melts model of my experiment number 18, or the fully melted sample. I took the composition of that silicate melt and then ran it through P-melts, since P-melts can only do the silicate melt. And I wanted to really see the difference of what having the silicate melt of the experiments, which had sulfur in it, to where P-melts did not have sulfur in it. So P-melts has an initial rise of CaO that's very different from what we see in experiments, but that's most likely due from the melting of CPX, which is absent in experiments. P-melts also has a much lower liquidus, which is most likely due to the sulfur in experiments, which raises the liquidus temperature. So here we're looking at Mercury mantle volcanic rock classifications. We see Mercury's surface on the right there in the gray ellipse, and its basalt to rhyolite composition. Models show a pretty wide range here from peak red basalt up to phonolite. And however, it's important to note that the right side of that ellipse, there's a significant portion of Mercury's surface that is not explained by these EH chondrite melts. And only one experiment overlaps with the Mercury results. All right, so this is a bit of a crammed figure, and I apologize. The gray crosses are from Messenger. They're the surface data points. And this is all of them that were taken by Messenger. So this is several thousand data points in this figure. And it just destroyed my RAM trying to make it. And so there's a few, the terrain classifications that you see there that are overlapped. I was unable to move. It just would bust up my computer. However, really important to see here that lower degrees of melting and more reduced area or environment show a higher Al over Si ratios, and higher degrees of melting and more oxidized show higher magnesium over silicon ratios. And if you also notice, most of our terrains align with the 0.55 composition, except for the high aluminum region. So another thing we can do is to use relative residuals to see model accuracy. So magnesium over silicon, aluminum over silicon, and calcium over silicon residuals are used here. And that way we can see just how close it is. If you look at the figures, the closer to the data points are to the line, the better the model fit. As you can see for magnesium over silicon and calcium over silicon, it's pretty accurately estimated, barring the HMG for the magnesium over silicon. But the aluminum over silicon model is not very accurate at all. Variations across Mercury's surface could result from mantle sources with variable SiO2, uh, and that can be affected by changes in FO2. So, I apologize. And another interesting thing here is that along with P melts, this relative residual model also agrees that most of the terrains occurred at melting degrees between 30 and 35%. All right, so this comes to the big question of the project, and that is, are EH chondrites Mercury's building block? Uh, Although great candidates, since most of Mercury's surface can be explained through them and through varying FO2 melts, there are some hurdles that we're going to have to get over. For one, the mantle actually needs to be heterogeneous in oxygen fugacity for this to happen. And so we're going to investigate that a little bit. Another hurdle centers around the volatiles that I brought up earlier. There's really high volatiles in EH and thus P melts. P melts is a closed system and kept those volatiles in there. So we need to be able to come up with a mechanism or at least evidence that volatiles have been lost on Mercury. We'll start with the mantle heterogeneity. So that could come from a poorly mixed mantle. When Mercury formed and the mantle and the core separated, the mantle up to the surface was known as a magma ocean or fully molten. And during that process, it could have not become homogeneous, but instead very heterogeneous. Uh, Sorry. Another thing we could do here is desulfidation processes, which is where sulfur is going to react with metallic iron or other metals to form sulfides and then thus reducing the amount of available oxygen and lowering the FO2 in the mantle. Another way is carbon exchange reactions or graphite-induced smelting, which is where graphite reduces the oxide or reduces oxides to metal and then releases as carbon monoxide or carbon dioxide, as these two formulas show here. Okay, so what about the volatiles? PMELS predicts a lot more volatiles than observed on Mercury, like we just discussed. So this must suggest that volatile loss on Mercury occurred on Mercury and during experimentation. We already covered in experimentation that volatile loss is inevitable. That's very common. However, we need to be able to prove it on Mercury, and there's a few ways that we can. One is hollows, or this top figure here, which is the sublimation of thermal decomposition of volatile-rich materials. In other words, a very volatile-rich area that then gets to the surface and then sort of pops and releases that gas. Let's see here. Here's an example from NASA of hollows on Mercury, so there is evidence of that. There's also transient atmospheres. The bottom figure here represents a volcanic or magmatic event that may, or we'll say, happen on Mercury. And they release enough gas for a very temporary atmosphere where those volatiles are slowly stripped away off the planet. Another thing that we've seen with elevated concentrations in the north and some in the South Pole is that sodium and potassium are highly mobile and have been easily released due to Mercury's surface. Could be from hollows, could be from volcanic eruptions. And once released, sodium and potassium are going to migrate along Mercury's exosphere and then redeposit in the poles. All right, so for future work, you may have noticed I talked about sulfur a few times and then not really did anything with it because it's quite difficult, and that's something that needs to be done in the future. Sulfur concentration is a lot higher in Mercury's crust than any other crust or mantle, as you can tell from this figure here. However, with low FO2 and high sulfur, sulfur solubility in magmas is going to go up. And as sulfur is increased in the mantle or in the melt silicate phase, more silicon will be reduced into a metal phase, as well as sulfides that are expected to form from that. So here are two different versions of Mercury's formation that people argue. One is that all that sulfur rests next to the core in an Fe-rich sulfide layer, although this is uh, argued that the other thing could be that there's a lot of sulfides present in the mantle, which we see a lot of around or in experiments. However, it is worth noting that in all of those metal blobs, there's networks of sulfur around them, so it's totally still possible that there is a Fe-rich sulfide layer around the planet. At low oxygen fugicities, it is also found that calcium and magnesium can be incorporated into sulfides rather than in silicates. Calcium and magnesium are also major rock forming elements. So if they're being taken into sulfides rather than silicate minerals, then that's going to change mantle mineralogy again as well. And then lastly, this project really only focused on one GPA due to restrictions from earlier, thus necessitating work at both higher and lower pressures to really see what's going on in Mercury's mantle. Due to Mercury's core being so large, the core mantle boundary, I'm pretty sure, is 20 GPA compared to where Earth's is much, much higher. So there's a very interesting mantle source to come from that. In conclusion, for my EH chondrite hypothesis, I think they're a great candidate for Mercury source material, yet there are discrepancies of elevated aluminum content as well as reduced volatile compositions, suggesting that there probably is additional processes or sources that contributed to Mercury's formation. For planet formation in general, oxygen definitely plays a pivotal role in the formation and differentiation of planets by being able to manage mantle mineralogy as well as mantle melting properties. Redox influence on mantle dynamics is controlled by Mercury's mantle likely exhibiting redox heterogeneity. And then this results from incomplete mixing from the magma ocean phase, or like we talked about earlier, with localized chemical processes like graphite-induced smelting or sulfide fractionation, which is also known as desulfidation. And then for future direction, Bepi-Colombo is on the way. He enters orbit in late 2025. We're going to get a lot more precise data, and there's more instruments, and we'll be able to see a little bit better of the internal structure of Mercury. And then for acknowledgments real quick, Osmo has been an amazing advisor and really helped me out. She, like she reminded, I do have two kids that I got in grad school, and she helped me figure out parenting as much as mentoring me on research. And then my committee members have been really helpful on pushing me with Sean and Christina and learning, asking me great questions. Taylor and Vanessa were awesome lab partners. And then lastly, the geology department and the rest of the staff were always incredibly welcoming and very helpful. And I never had any issues with anything. Thank you, and questions?
Thank you, Richard. That was very good. Thank you. So yeah, and let's all first unmute our mics and we can give a big round of applause for Richard. Yay. Okay, so now we're gonna open the stage for questions. Please, we're gonna start with questions from students. Is there any question from students? Open the chat too here.
I have one question. I think I may have missed it. When you were doing the graphs and you were showing like all the different compositions and then you put the red box over the gray box, what was that red box displaying?
One sec, let me reshare the PowerPoint. That would help. All right. Are you talking about right here?
Yes. No. Yes.
Are you talking about right here, the smaller one? Oh, you can't see my mouse, though. But
Yeah, I can. I can see the mouse.
oh, okay. So this area, I just wanted to be able to show what P-melts does from 100% melting up to about 30, 35% melting here, and just show that this is really the only area that P-melts can predict between the 0.36 to 0.07 ratios.
Okay. So on the next plots then, is that the same, like the P-melts is what you're able to get out of it? Oh, yes. Okay.
Yeah, so P-melts is going to be the red polygons.
Okay.
They're going to be the complete range of variable oxygen fugacity that covers the surface. You can definitely tell here in this calcium graph, there's a lot of the surface left to be figured out.
Oh,
But the high aluminum region here is a little tough, but you can get most of it in the aluminum graph.
okay. Thank you so much.
Yeah, thank you.
I had a question about, you said that EH chondrites, what set them apart from whatever else is that they did not experience igneous differentiation. What does that mean?
So it means that they stay essentially, it stayed small enough. I'm trying to think of the best way to describe it. It stayed small enough to not experience any kind of differentiation or melting. It's just the conglomeration of dust and minerals from space.
Okay,
Does
thank
that
you.
make sense? It's like
Yes.
once it gets big enough to be rounded or for anything else to like form, it changes the mineralogy of the whole rock.
Okay, sweet. Thank you.
Mhm.
All right. Are there any questions from everyone, from the community, especially maybe? Sue?
Yeah, I think there was something that I missed in your discussion of the previous slide. Could you go back one? That one, yeah. So you had mentioned that the gray area is where, or that grayed in area was where observed rock types or inferred rock types that there were rhyolites on Mercury's surface. Did I understand you right?
Yes.
And so then why do you think if I'm understanding things right, your models don't predict rhyolite? Maybe I missed something in your explanation. So all those, the dacites and the rhyolites, that's a significant silica range.
No, that makes sense. The reason that I don't think it covers the right side of this area here is mostly just because the models don't cross into those fields.
Mm,
Other than it just seems kind of odd because they're really high SiO2 weight percent for rhyolite, obviously,
right.
and that the EH chondrites have so much silicon in them, you would expect them, especially these lower SiO2 ratios, to be able to make it over there. I'm I'm not really sure. That's a great question. I'll have to think about that a little more. I've really just been
So,
thinking about it kind of plainly with just the lines, but there has to be more there.
yeah, so basically, if I understand what you're saying, is that those rocks are there, but the models just aren't able to predict them.
Oh, yes, that is what I was trying to say.
Yeah, okay. Interesting. That is a really interesting problem. And first of all, I didn't even know that there were dacites and rhyolites proposed to be on Mercury's surface. So that's interesting in itself. Thank you so much, Richard. Really nice presentation.
Thank you.
Richard, just to follow up with Sue's comment, like that gray field, it's very much like Earth, right? So if you, I can't remember exactly what oxygen fugacities you had for your models, but if you did a more oxidized model, would the fractionation path actually sort of increase total alkalis more slowly and produce a rhyolite?
Yes.
Yeah.
And that's something I probably should have added that I meant to for future
Mm.
work was also talk about if there is heterogeneous oxygen fugacities in the mantle making these
Right.
sources, there might be oxidized versions as well. Like it doesn't have to be just reduced in the if they're pockets. So
So
it'd
that
be like,
actually, oh, sorry, keep going.
oh no, I was just saying that I agree with you that a more oxidized uh, environment would probably create that rhyolite field.
Yeah, so that actually kind of goes into my one question I had, which I think is really broad, and it's and hopefully you can just speculate on this, but your thesis was obviously really focused on testing the hypothesis of whether or not EH chondrite and then variability in oxygen fugacity there could produce the compositional variability of Mercury's surface, right? And so part of your answer was like, well, not exactly, and there are some other reasons, but have you then considered that maybe the mantle is heterogeneous compositionally and not just with oxygen fugacity? So are there other chondrites that could also be there? Like, could there be multiple compositional components, not just multiple oxidation states in the mantle?
I think you have to say that that's a high possibility, considering that these, at least the models of this particular insight chondrite show that it doesn't cover all of it. That's
Yeah.
also assuming that there's a lot of insight chondrites in Mercury to begin with, which I think there is. But I think that you're onto something there, that there probably is something else that comes into play. Whereas similar to like Earth is very similar to an EH chondrite.
Okay.
So I'm trying to I wish I could just like speculate on which particular chondrites just to speculate, but there has to be some other formation or part of the formation process that happened, and it probably is separate source material or that's a pretty interesting question.
Cool, thanks.
I have a
Yeah,
question.
and
Oh, sorry.
just to add, sorry, just one last thing to say. So N-side chondrites are the chondrites that are the most enriched chondrites in silica. Actually, you cannot have more silica than EH chondrite. And yeah, and so I think that what happens with these rhyolites and dastites and mercury, I'm pretty sure there's more than just equilibrium melting, batch melting that have been modeled here. I'm sure there's like, there might be some different, more complex differentiation processes happening around those areas. And there's a lot more to do, fractional crystallization, and more complex processes than just batch melting of a chondritic mantle. But this is just the very beginning of study on any chondrite or any mantle sources. But yeah, these are really great questions. And so so Melissa had her hand raised.
Yeah, great talk, Richard.
Thank you.
Thanks so much for your good explanations. I was also had some questions about the EH chondrites as the kind of building blocks here in the starting composition. Just thinking about Mercury's position in the solar system and its proximity to the sun and the higher temperatures it would have experienced, and what materials may have been available in the early solar nebula as condensates versus volatiles. I was just curious what you think about an EH chondritic composition with respect to Mercury's particular place in the solar neighborhood, and if we would expect compositional gradients as in the terrestrial planets based on their proximity to the sun, and whether the EH chondrite composition is consistent with that.
Thank you. It's a great question. And you're right. I meant to say that in here to say I definitely powered through that a little too fast. But the going into here, the distance from the sun heliocentrically, the denser elements came, or like you were saying, the denser elements came in closer to the sun during the formation of the solar system, and then lighter elements went out. So the EH chondrites are higher in metal, which is why Mercury has a larger core than anything else, because it has more metal in it, as well as higher volatiles because it's closer to the sun. They have a higher condensation temperature. I might be speculating a little bit there, but there's a lot of volatiles in EH chondrites which are close to the sun. What was your other question on?
Oh, I think that gets at it. I was just curious
Okay,
about
sorry. I just blanked a little bit.
compositional gradients in the early solar nebula
and
how that fits in with the EH chondrite hypothesis.
Okay. Then to answer that a little better, N-type chondrites have more metal and are closer to the sun and more volatile rich, which is also where Mercury is. So since it's closest to the sun, I think the N-type chondrites have the greater argument solely based off of location and metal content. But I think it fits in pretty well. I just feel like maybe with movement in the solar system or something, a different set of chondrites helped make that field that we can't observe. I just don't know what chondrites they'd be, whether H or LL or.
Great, thank you.
Sean?
Good talk, Richard. Thank you. One question, can we go back to the rock classification diagram? I was just wondering too, like how much do you think, so you have these like really alkaline melts, and I noticed too, I think somewhere on your feldspar plot, you're getting albitic feldspar with things like pyroxene and olivine, which seems kind of counterintuitive. Like I'd expect more anorthitic feldspar. So I just wonder, how much do you think for these highly reduced bulk compositions that you're putting in, how far are you pushing P melts outside of the experimental data and the solution models that it's designed for? And it's like, are you seeing some limitation in the tool here versus
Oh, yes, for
something
sure.
geologically reasonable?
That's a great question. Thank you. And these melts, so for the blue line, which is the most reduced model, it gets up to 30% alkali at 10% melting. You can see where the 20 is compared to where these 10s are here. But in terms of pushing P melts, I actually had to talk to the makers of P melts a few times through email, and they helped a lot with getting us in there. We originally started not putting any iron or FeO in the starting composition, but P melts requires FeO to run. So my first models that actually I showed you for the proposal were like completely wrong because I didn't put any FeO to start with. But we ended up doing a halfway percent, which is lower than that 1.5 average that Messenger sees. And so we're pushing this pretty far, but I'm pretty comfortable in saying that these are within the scope as long as they're not going over 1 GPa. And I don't think I can really go past 20 weight percent silicon metal. So that would be just way too much MgO in the melt and not enough SiO2, and it kind of breaks down pretty quickly.
Great, thanks.
Shay?
Hey, I had a quick question regarding your choice for the 1 gigapascal. I know you mentioned that P-Melts runs fairly well at 1 gigapascal. Was there another reason why you chose 1 gigapascal? I may have missed it.
No, that's fine. The main reason is that red line there represents the 1 GPa line. And all the terrains there are listed younger, closer, and older at the top. And all of them cross over that 1 GPA line with
Okay.
the MVP kind of resting on it. So I just figured that was kind of, since it averaged out to 1 in the end, it made the most sense. Since at least for comparing the models, I wanted to keep pressure the same and just change temperature and FO2 because it was already getting somewhat complicated trying to understand what I was doing to begin with. And so I just kind of just stuck with the 1 GPA.
Right, perfect. Thank you. I did miss that.
Thank you.
So we have a question from Alex on the chat here. I'm going to read it to you. I was wondering about when you said sodium and potassium migrate to the poles, what did you mean? I know this isn't a direct focus for your project.
All right. So what I'm talking about there is so Mercury has a magnetic field as well as a small exosphere. During micrometeoroid impacts, as well as those volcanic events where sodium and potassium are released into the atmosphere, they will migrate in the exosphere and then be redistributed on the poles. And I think I was really bringing that up as just another mechanism to explain why maybe we see some of the depletion in some of those areas that maybe they got the sodium potassium kind of got up and moved during the volcanic events when they were released. Because some areas in the northern hemisphere show higher concentrations than others. In particular, if you're looking at up here, I'd have to triple check, and Ozma could probably correct me, but the low Mg northern plains or this blue area here, I'm pretty sure has more potassium than the other regions. I know it's measured by ppm there, so it's a little difficult, but still.
Yeah, that's right. They have more sodium and potassium at the North Pole. And we actually even detect some sodium in the exosphere. So exosphere is like the atmosphere, but a lot less dense and a lot less molecules in there. But so we know that some sodium is present in a gas form in the exosphere. What we think is because of how the equator is a lot cooler than the poles, you might vaporize more of the sodium and redistribute on the cooler areas like the poles. But so far, Messenger has only measured compositions for sodium and potassium in the northern hemisphere. So now the new mission, Bepi Colombo, is going to be able to map better the southern hemisphere, and we're going to see if we have the same process with enrichment of those alkalis in the southern pole, in the South Pole. And then that might actually just confirm a little bit, maybe just confirm the fact that volatiles are redistributed on Mercury and might be more enriched in the poles because of differences of temperature between high and low latitudes. I hope this helps a little bit. Otherwise, it might also just be a signature. If it's not the case, then it might just be a signature of terrains at the North Pole, which are the ones that are rhyolites and dacites, actually. So, you know, for rhyolite, yeah, so they might just be alkali-rich rhyolites. So, yeah. So are there any other questions?
I have one more. Richard, do you mind going back? You had a figure where you compared your P melts to the experiments. Yeah, that one right there. So one of the things that I thought was odd, and maybe this has to do with some of the contamination in your experiments, but the 1400 degree experiment has less melt than the 1300. And one of the things you mentioned was that it's less than the P melts models, but do you think that's actually, should it not be more than the 1300 degree experiment?
Yeah, it definitely should.
Yeah.
I think that a lot of future work ideas would probably be a lot more experiments with
Yeah.
the better casings we have for the graphite capsules now.
Yeah.
There is a lot of barium contamination, and I know you already read my thesis. Thank you. But the barium it looks like it doesn't affect any of the mineral formation. I say it doesn't affect mineral formation. Doesn't affect mineral composition, as in there's not really any barium going into the minerals.
Yeah.
However, some samples like this 1300, the second from the left, it has like 17% barium in it. I included these because they still follow a decent trend. I made sure to put that in there that they have the barium, but it's kind of tough to tell. Similar to these kinds of projects, you need a lot of experiments to have like a lot of good data, and you're kind of limited when you only have 7 data points.
Yeah. And it also wasn't related to quenching or anything, do you think?
So actually, a few of these are related to quenching. The 1600 experiment had some issues with that, but the lower temperature ones are the ones I had to worry about because I had to leave them running overnight. And on one particular sample, which is that 1300 that has the weird melt, or more melt than the other 1300,
Yeah.
it whenever you quench it, you're supposed to remove power and hold pressure. Like you can only change one thing. And I came in and the pressure had dropped, and so I quenched it because its time was up and used the sample anyway. But there definitely was about a 0.2 GPa difference, which is probably enough.
Yeah. No, experiments are so challenging.
Yeah.
So I appreciate, you know, and I think your thesis really sort of outlines all of those challenges really nicely. But yeah, here I just really wonder if there should be more melt in some of these. But yeah, for someone else to follow up on.
Yeah, it's quite the step up there from 1500 to 1300.
Cool, thanks.
Yep, thank you.
Is there any other question? All right, cool. So let's thank again, Richard. Let's say congratulations, Richard. It was very good. Thank you. Congrats.
Thank you.
Nice work.